Hello. Hello everyone, welcome back to the channel. So today we are going to solve this question called the 13th labor of Heracles from the Codeforces. Actually it is a very nice question from this Goodbye 2020 round, and let us take a look at the question. So in this problem you are given a tree with n weighted vertices. A tree is a connected graph with n minus 1 edges. Let us define its k coloring as an assignment of k colors to the edges so that each edge has exactly one color assigned to it. So note that you don't have to use all k colors. So a subgraph of color x. So question is slight trickier. Question in the sense the problem statement. You have to read it carefully. So give it a try before listening to the solution. Give it a try uh, on your own to solve this question. So yes, a subgraph of color x consists of these edges from the original tree which are assigned color x, and only those vertices that are adjacent to at least one such edge. So there are no vertices of degree 0 in such a subgraph. The value of connected component is the sum of weights of its vertices. Let us define the value of a subgraph as a maximum of values of its connected components. So we will assume that the value of an empty subgraph equals 0. There is also a value of k coloring which equals the sum of values of subgraphs of all k colors. So given a tree for each k from 1 to n minus 1, calculate the maximum value of k coloring. Okay, so yes, basically you are given a graph. So let us take a look at the sample test case. Yeah. So listen, this is the first node, this is the second node, they both are connected. This is the third node and this is the fourth node. Values of these nodes are 3, 5, 4 and 6. So for k is equal to 1, we only have one color, right? So for that one color, we will color every edge by suppose this blue color. Blue color, okay. So for k is equal to 1, our answer will be just the sum of this 5, 3, 4 and 6. So it will be 18. Okay. What about k is equal to 2? So for calculating answer for k is equal to 2, suppose we have red color at our disposal, red and blue. So your instinct would be like, hey, listen, if I draw an edge, red edge here instead of blue edge, my score will increase by 4, right? My score will be increased by 4 because our connected components or subgraphs would be like this: 2, 1, 3 and 3 and 4, right? So this 4 in the third node is both in the subgraph of blue and red color, right? So our value of our answer would be increased by 4. So if I draw that edge here, okay, if I drew that edge here, then our answer would be increased by 3, right? But I want to maximize my answer, right? I want to maximize the value of my k coloring. That's why I am drawing the red edge here. Okay, so that is basically the point. Okay, so your first intuition is that you will color the edge containing the vertex which is maximum possible. Okay, and one another thing, look at these leaf nodes, right? So no matter what subgraph they are in, they won't be counted twice, right? So if I color this edge as black or whatever it is, black, purple or white, don't know, but they won't be able to increase the answer, right? So all uh, all all the thing about answer lies in these non-leaf nodes, right? Okay, so that is basically the first observation. So answer depends only on non-leaf nodes. Okay, okay. Now, how about suppose this is our graph. One, two, three, four, five, six. Okay. So suppose some values are associated with it. 2, 3, 4, 5, 6, and value of this guy is suppose 10, right? So okay, let's make this guy 12 and this guy 2. So what my intention states is that I want to draw an colored edge, means the extra edge of different color, not extra edge, I have to remove one edge and draw an edge of different color so that it includes this vertex, right? Because it has maximum value, right? And one more thing, so if you notice here is that, so suppose this is some graph. Okay, so this is some sub tree of graph. So what I can notice is that I can color this edge with, suppose, let it be black, this will be red, this will be green, okay, this will be green, this will be yellow, and what else color? Violet. So this will be violet. So what I can notice is that my this vertex can contribute at max to at max 5 times, right? So for these 5 colors, so basically this is its degree, right? So this is observation number 2. Observation number 2, that a node will contribute degree of node times, right? At max, okay. It won't be larger than that. Okay, so this is one more observation. And one more thing is that, suppose you draw edge here. Okay, if you draw edge here, now my black colored subgraphs would be this and this thing, right? So to contribute to the K coloring, I will take this component, right? This component, because its sum is 5 plus 4 plus 3, 12, right? So, and sum of this is 8. Okay. So if I color it in this way, my answer will be 12 plus this 3 plus 12, right? This is red component. So this is basically the red component. This thing is black component and this thing is black component. So this is the sum of black component, means the value of black component, because we have to take the maximum of both, right? 8 and 12. So 12 plus 3 plus 12. Okay, let me change the color. 3 plus 12. So this is contributed by the red graph, red subgraph, and this is contributed by the black subgraph. So my answer would be 12 plus 12 plus, what you can say, 27, right? So basically what I can see is that this subgraph is wasted, right? This subgraph is wasted. It didn't contribute to my answer. So what I can do is that, so this is the most crucial observation. So yes, observation number 3. So this is the most crucial observation. So, okay, if I draw edge here, what if I draw red edge here and here as well? What will happen? So basically, what will happen is that, so let me take this part. Okay, wait. No. Wait, let me draw it again. 1, 2, 3, 4, 5, and 6. So if this edge is colored red, this edge is colored red, this edge is colored red. So values were 12, 2, 3, 4, 5, and 6, right? So if I color these three edges as red, then this thing forms a red component and this thing forms a black component, right? So basically the components will be splitting like this, right? Oh wait, what am I doing? 1, 5, and 6. So basically now you can see that this part is counted and these nodes that were wasted are still contributing to the answer, right? So what I can observe is that colors, so this colors form only one connected component, okay, right? So this is the most crucial observation. Every color will have only one CC. CC means connected component, okay. So these are the three key observations. So my solution would be like, I will store all the values. Okay, wait. Why is this A capital? Store all the values which have degree of its vertex as greater than 1. I will store those because this comes from our second observation. Wait, not second observation, this comes from the first observation, so that only the leaf nodes won't contribute. And secondly, I will store the multiple occurrences, right? Store the multiple occurrences of them. How many multiple means the degree of it, right? So store multiple occurrences based on the degree, based upon the degree of that value. Okay, so this comes from the second observation, right? And then finally we will sort that vector, reverse it. Okay, how can I represent it? So reverse it and just take the elements from the start. So just take the elements from the starting. Start to end. And keep it adding into your answer. So this is basically the solution. I hope you understood it. Let's hop onto the code. So code is pretty straightforward. uh, for k is equal to 1, answer is directly the sum of all the values of vertices, then taking the input and recording the degrees of the vertices. And finally, if degree is 1, then we won't consider it, right? And if degree is greater than 1, we will consider it. And why degree of I minus 1 means, so when you are calculating answer for k is equal to 1, you have already taken it once, right? So you have already taken it once. So that's why degree of I minus 1, and storing it in